Hello, everyone. I'd like to thank you all for coming out, especially our friends from France. My name is David Ring, and I went to France this past summer and worked at the ILL, and I'd like to share with you the experiments that I did while I was there. So I'm part of Act 1, which is concerned with water purification and collection, and I will be showing you the membranes that I attempted to make while I was there in France. So the motivation for this project is that during natural disasters, you have a significant impact to water resources. In fact, the United Nations says that all natural disasters have impacts on water resources. So you can imagine that we want to create some sort of device that would allow us to remediate these impacts. And it would have to have certain characteristics, such as being fairly simple and easy to manufacture. It would have to be compact so you can transport it. And it would also have to, and this is very crucial, produce enough water at a potable purity that it would meet the demands in the area. So the idea is to use membrane filtration, and one of the reasons is that it meets most of these requirements, and it also can filter out a wide range of contaminants, anywhere from bacteria and viruses all the way down to very small ions. And so this is about 5 orders of magnitude of contaminant sizes. And so the one problem that membranes do have is that there's a trade-off between the purity and the quantity that they can produce. So the two terms you can think about are permeability and selectivity. And so what this plot is showing, and this is all done with gases, but it also applies to water. What this shows is that there's this upper limit in this trade-off, and over a period of about 10 years, we've only been able to push it a very small amount. However, if you take a pure polymer film and you start putting nanoparticles into it, what happens is that this permeability and selectivity trade-off is pushed upwards, and so you can produce a purer, or you can produce more of a pure product with the same area of membrane. And I'd like to draw your attention to the fact that this is plotted in terms of weight %, and if you convert this into a volume fraction, you can see that there's room for improvement in this membrane performance, and if you extrapolate this volume fraction out, you can see that there could potentially be a very significant improvement. And so we would like to try and create membranes with very high filler fractions to see if we can achieve this sort of performance. So the previous work that has been done with this is to take polymer and nanoparticles, in this case a short chain polymer, and to perform this capillary rise infiltration process that Neha talked about. And we have demonstrated in the past that we can generate very high filler fractions of nanoparticles. If you look at the dynamics of this process, the inset here shows that it follows a very particular scaling, which is consistent with this equation called the Lucas-Washburn equation, which governs capillary infiltration into different media, including, say, water and sponges. Now, I would like to work with a slightly different system, and the reason for this is that we want to be able to do this process with many different types of polymers, including very high molecular weight polymers. And so the idea is to try and see if we can achieve this infiltration with high molecular weight polymers and study the dynamics of these polymers. So the reason why we have questions about the dynamics is that if you take a long chain polymer in a polymer melt, you can imagine it would have a very large radius of gyration, and when it infiltrates into these nanoparticle packings, it would have to change its configuration and lose that entropy, and so it could be very difficult for it to work its way into these nanoparticle packings. And so, using some techniques such as electrometry, we've been able to observe that some infiltration occurs. But we would like more information, more insight into the mechanism and final structure of the film. And so this is where neutron methods come in. And the Institut Langevin in Grenoble has a very nice resource for doing neutron experiments. They have a very nice facility there. So in case you're not familiar with neutron reflectometry, if you take a neutron beam and skip it off the surface of a simple or a very thick layer of, say, a polymer, the beam is reflected and there are no interference patterns picked up. However, if you have multiple layers that have different, or that scatter neutrons differently, what you can have is a series of out-of-phase reflections which create a interference pattern, which can then be used to describe the thicknesses of these layers. And I've shown several different curves here to indicate that over time you can observe the changes in this reflectance and thereby observe the changes in the thicknesses of these layers. So the initial configuration would look something like this. You just have a simple bilayer. And you could imagine that there are perhaps two different mechanisms for infiltration to occur. The first I'm calling Lucas Washburn because it would be a simple infiltration with a clear front. And the next I would call uniform, or perhaps you'd say backfilling. It's very slowly filling in the voids between these nanoparticles. So this plot on the bottom is a selection of data from before and after the infiltration process. So on the y-axis we have what's called the scattering length density, and that's an important property because it gives information about the composition of the film. And so what we can see is that the SLD increases in the nanoparticle layer, and the thickness of the polymer layer decreases. And this is important because it shows that there is indeed infiltration, and that we can observe it with the neutrons. And so now if we look at the evolution of these samples over time, one very interesting thing that occurs is that after, or in this first region, up until the black line, there is infiltration of a thin layer that I'm calling the composite, and it's about the thickness of a nanoparticle. So what that seems to show is that there is a full infiltration in this first layer of nanoparticles. And interestingly enough, the nanoparticles above it seem to be then covered in polymers very gradually. So this is not a Lucas Washburn type behavior. There's no clear rising front. And it's interesting to see that there is a different process by which these high molecular weight polymers infiltrate. So I'd like to conclude by saying that I've been able to show that high molecular weight polymers don't follow Lucas Washburn scaling. And one issue that comes up in the data is that it's not clear whether infiltration has stopped yet. So the ongoing work that would be important is to use complementary techniques in order to observe the final layer structure. And as Neha has shared with you, she is working on solvent-driven infiltration and would like to look at or observe that process with neutron reflectometry. And I would like to share with you one last piece of work that I have been working on, and that is molecular dynamics simulations to observe the effect of confinement on this infiltration process. So, as I said earlier, if you have a large polymer, it undergoes a lot of confinement in these voids. And so if we take a very simple system and infiltrate it with a polymer, in this case just a simple capillary, we can observe the infiltration and we can see how changing the radius of this capillary affects the infiltration. So with that, I would like to thank all the people who made this experience possible, and also my colleagues in the lab. And I'd like to take any questions.
Questions? So I want to ask a question. So when you have a tube, you just have one type of curvature, right? The other radius of curvature is 0.
Yes.
Can you implement, I guess? But inside these composites, you have both positive and negative curvature. Do you have any idea how that's going to affect?
So This is sort of a first approximation system, and the idea is that we can study confinement in this very simple system and gain some insight, and we could say move to other types of capillaries after that, such as ones that had a change in cross-section, where you would introduce an extra curvature.
Could you show your reflectivity again?
Sure.
Is one of those a fit? I want to see your scattering length density profile. Did you show a fit on the previous slide of that?
Yes.
So what's the fit to the filled? Just explain those three lines, like the three different colors, I guess.
So they're data at different time points, and it's just a multi-layer model that's, I guess it's called the Abels formalism, and it's fit to this particular range of data. And
green is the initial. Which the initial?
Green is the initial.
The initial, and then you're looking at two different snapshots in time.
And your model is a mashup between the Lucas Washburn and the uniform, because there's a little bit of Lucas. There's a little bit that's fully filled, and then there's a lot that is just partially filled.
Yeah, it seems like that first layer wants to fully fill, but then the rest of it, it's gradually filling.
And you can detect the three distinct layers.
Yes.
You have three layers, all green, fully filled green in the particles, and then the particles not fully filled with the polymer.
Yes.
And what roughness factors did you put into that? Do you remember?
I don't remember. Some of them were allowed to vary. Yeah, it depended somewhat. I'd be happy to go over it with you some other time if you would like.
So it's not about your experiments. My question is more about like the motivation. Do you have any, or can you explain to us, or do you have any idea of why nanoparticles enhance the perm selectivity of the membranes?
So there's so there's been some debate about this. The paper that I showed that they had that plot where the perm selectivity goes up. They claimed that there were these void spaces around the nanoparticles which enhanced the selectivity while allowing the permeability, or enhanced the permeability while allowing the selectivity to stay. Basically void spaces. That's what they said. And there's another paper that addressed this further, and they showed that you don't just need nanoparticles. You need to actually have a disruption of the polymer, the way the polymer packs around itself. And so the nanoparticle, so if the polymer is stiff enough, you can get the nanoparticles disrupting that packing.
Okay, with that, let's thank David one more time.